Swayam Prabha. Digital India. Educated India.
Good morning to you. We are now on to lecture 12 in the second module on the review of basic structural analysis, part 2. We will be covering displacement methods, which we started in the last session. We will continue with the introduction and get into slope deflection and moment distribution methods. So this is covered in part 5 of this book on structural analysis. If you recall the last class, we actually learned quite a bit about the meaning of stiffness matrix and how to derive the stiffness matrix from first principles. You recall that? Now, can you write down the stiffness matrix for this, given that all the three spans are identical? That means they all have the same L and they all have the same EI. What will that matrix look like? Can you do it? It will be a symmetric matrix. What will it look like? Okay, so that's right. Now let's solve a problem from first principles. Let's take this beam and let's say it is subjected to F1 equal to F2 equal to m naught. Okay, so two concentrated moments applied at the joints B and C, and the challenge is to analyze this beam completely, which means find the bending moment diagram after finding the unknown rotations d1 and d2, theta b and theta c, right. So the stiffness matrix for this is this. I presume you got this from the last slide, right. How to proceed from here? F1 is known, F2 is known, both are equal to m naught. So just invert the matrix. Will you find out theta A and theta B quickly? So inverting a 2 by 2 matrix is simple. The constant EI by L gets inverted to L by EI, then the diagonals get, then you have to find the determinant, and 1 divided by the determinant comes outside as a constant. The diagonal elements, the main diagonal gets flipped over, the cross diagonal elements you will attach a negative sign. Am I right? Will you get d1 and d2 for this problem? The determinant is 60. Is this okay? It's simple. So in a jiffy we got the rotations theta A and theta B with the help of the stiffness matrix of the structure. Now that you know the displacements, it's kinematically determinate, can you find the bending moments from first principles? Can you draw small sketches showing the kind of end moments you get when you apply only d1 with d2 restraint? Okay, the answer is both d1 and d2 are equal to m naught L by 10 EI, which means EI by L into d1 is 1 by 10 m naught, which is 0.1 m naught. Is it clear? This is straightforward. Now let's draw the two pictures, the free bodies showing only the moments. Okay, you will actually have shear forces. Let's not draw it right now. Can you fill in the blanks? What are those end moments? Remember in the last session we worked them out. They are either 4 EI by L or 2 EI by L in this case. The carryover moment will be 2 EI by L. Remember? So this is what it looked like in this problem. All the EIs are constant and all the L's are constant. So do you agree that this will take this form? It's 0.2 m naught, 0.4 m naught. That's it. You have only two options. And in that matrix multiplication you have to add up the contribution of both D1 and D2. So you can physically add it up. Can you construct the final bending moment diagram with these free bodies? What will be the moment at A? 0.2 m naught. Will it be sagging or hugging? It's sagging. What's the moment at B? You have to add up. Huh?
Sagging.
At B? At B? It's how can it be? Look at look at this free body. Look at the free body due to D1. You agree? At this junction you got 0.4 m naught, right? You got 0.4 m naught. This is what you get, right? This is what you get. So for the element 1, that's a bending moment diagram. When you apply D2, nothing happens to element 1 because you have restrained the joint B, nothing spills over to the element 1. Is it clear? You should have no doubts about this. I am adding those two free body diagrams. That's superposition. I am saying apply the effect of D1. Well, let us look at it from a pure displacement point of view. In the displacement method, what is your kinematically determinate primary structure? It is a structure where you arrest all the rotations. Then you allow one at a time. So we are now allowing only D1. When you allow D1, you will have bending moments only in elements 1 and 2. You will not have moments in element 3. When you allow theta C, which is D2, you will have bending moments only in elements 2 and 3, but nothing in 1. Then you just add up the contributions. Is it clear? So in element 1, you will get bending moments only due to D1 when you are doing superposition and not due to D2, right, in the restrained structure, in the primary structure. So what do you get in D2? Yeah, what do you get in 2? In 2 you will have to add up both the contributions, or in 3 it will look like this, right, it gets flipped over, and in element 2 0.6, 0.5. Does it make sense? So we did this from first principles. And look at the deflected shape, it is more or less showing the right thing. You get hogging in some region, you get sagging in some other region, there is a point of contraflexure. Does it make sense? So we did something from a completely different perspective, a fundamental approach. Is it clear? Now this is not how the subject of displacement methods evolved. The whole concept of stiffness matrix came later. George Maney discovered, or invented if you wish, the slope deflection method, where he made you solve a series of simultaneous equations and get the results very quickly. But this is a much better understanding where you really know what is happening step by step. Now this was an easy problem in the sense the loads were given to you conveniently as concentrated loads F1 and F2. In reality, the loads are more likely to look like this, right? These are intermediate loads. How will you handle this problem with the same stiffness matrix, right? So we are getting into the formulation of the stiffness method of analysis, which is what we need later when we do matrix methods. How will you handle this problem? It was easy enough to analyze the previous problem because the moments were all conveniently nodal moments, right? F1, F2. Here F1 and F2 look like they are 0, but instead you have intermediate loads, arbitrary loads, P1, P2, P3. How will you handle this situation? I want you to
Shift the P1 to support B by adding moment and force.
How do you do that? So you are right. Somehow you have to convert this problem to the previous problem. That means you have to get an equivalent F1 and F2, because you can solve by the stiffness method only if you have joint moments. How do you do that? How do you do this conversion? It is called equivalent joint loads. How do you create that situation? And it is nice to to go through it conceptually. I want you to see how learning takes place. There are two kinds of learning. One in which you see the big picture and you develop the concept. That's a higher level of development. The second is somebody does that work for you and you just apply step by step. Step 1 you do this, step 2 and you solve and you get the answer. We would like you to develop both abilities, right? You see the big picture, you lay down the map and you also know how to get into the detail and crack the problem, and we will do that here. So I want you to go back to the force method of analysis, where what did you do in the force method of analysis in the last row? Yeah, please stand up and tell me, please tell me how did you solve the statically indeterminate problem by the force method. You know it, we have done this before. The problem is statically indeterminate, right. So we know how to solve only statically determinate problems. So what did we do?
Cut in the middle of the.
Don't take any structure, we are talking generic. In a truss you don't need to introduce any, so talk generic. Somebody else can answer.
Use it.
Stand up and answer.
Conjugate method we can use.
No, in a truss you can't use conjugate.
In a truss.
So talk generic. What is the basic principle we follow? One of you girls, stand up and answer. Choose a primary structure. So that's the first thing. You are comfortable with statically determinate structure. So somehow make the structure statically determinate. How do you do that? By identifying the redundants and providing releases, which could include providing hinges. That's one way of providing a release. Okay. So sit down. So we did it there. We can work only with a statically determinate structure. Then we sequentially apply loads including the redundants on that primary structure which we can handle, and we do superposition. So you can apply the same concept here. So what is your primary structure here? Is it a statically determinate structure? No, this is a displacement method of analysis. What's the type of indeterminacy here? What's the type of indeterminacy? Kinematic. So what is your primary structure?
Fixed beam.
A kinematically determinate structure is one in which you arrest the rotations. If you arrest rotation at B and C, you don't get any movement there at B and C. You will get deflections, but you have arrested the two unknown. So you see there is a similarity in the two approaches. So shall we do that? And this is something we can handle. So we arrest it. The moment you have arrested those rotations at B and C, there is no interaction between those three beams anymore, right. You can actually separate them out and look at them independently, and you are supposed to know everything about kinematically determinate structures. So you must know the end moments, the fixed end moments, and we know how to do that. We can actually show you tables which can handle any type of loading. You can get a table of fixed end moments, but we at least should remember what is a fixed end moment when you have a concentrated load at midspan or a UDL, which are the most common cases. So we know MFAB, MFBE, MFBC, MFCB, MFCD and MFDC. Is it clear? We apply some formula and get those moments. Now what do we do? Follow the same procedure we did in force method, but using displacements. What do we do next logically? There what did we do? We satisfied compatibility. Here we have to satisfy equilibrium. How do you satisfy equilibrium? Right now you do not satisfy equilibrium because you are getting moments at B and C, but in the original structure there are no moments. So what should you do?
Equate the moments. That is.
How do you do?
Keep the moment for this and analyze separately without moment. Keep couple of moments.
No, you've got these values. Let's say at B you have MFBA and MFBC, clockwise positive. What should you do?
To make it 0, we have to introduce a moment and then.
Perfect. You have to make that thing 0. Then only you will satisfy equilibrium, because in your original structure MB is 0. How do you make it 0?
We will make it 0 by adding moment and also subtracting moment in the separate case. And
No, you need to do only one case. So you can do this. Go back to the old beam. Apply nodal moments F1 and F2, which is the negative of the moments that accumulated there when you artificially arrested those rotations. Now does this make sense? Okay, so the argument is, when I add up this picture with this picture, I get back the original picture, right? I am satisfying equilibrium because there are no moments. I am adding these two and subtracting them here. I am putting it in the opposite direction here. So when I add up everything here, I get what I get here. In this case there is no nodal moment here, and there is no nodal moment here. You got it? This is a powerful method. Now do I know how to handle this problem? We just did it. So we cleverly converted intermediate loads to equivalent joint loads, cracked the problem, solved this, and after you get the solution of this, you add up the response that you get here, and that is a complete solution. So you have to add up the bending moment diagram or bending moments that you get from the fixed end condition to what you get from the nodal moment condition. Is it clear? You have a doubt?
So basically we are using the we are arresting the rotations at B and C for
to get the primary structure and then releasing them, and you can do it actually one at a time. We saw it. If you do everything together, you need a stiffness matrix to help you out. Is it clear? Does it make sense? There is another interesting point I want you to note. These are called equivalent joint loads. Okay, F1 and F2 here are called equivalent joint loads. They are joint loads which give you the same rotations as you had in the original structure at the coordinate locations identified. The D1 and D2 that you get by analyzing this structure, which you can get from the stiffness matrix, will be exactly equal to the D1 and D2 from in the original structure. Why? Because this is equal to this plus this, and D1 and D2 in this system is 0. So that is a powerful concept, and this is the real foundation, the real basis of displacement methods. All displacement methods follow this path, though sometimes in textbooks they teach them as independent disconnected chapters. You study moment distribution method in one chapter, you probably learnt that way. You study slope deflection method in another chapter, then you study stiffness method in a third chapter. They are like short stories in a novel rather than a novel where the chapters are continuous. So we are going to look at all together because they are all the same. They are all the same. This is the underlying concept, and you can use this beautiful equation, which is essentially an equilibrium equation which relates forces with displacements. So let us summarize. The first step in displacement method is to identify the degree of kinematic indeterminacy, take advantages of modified stiffnesses and reduce the number as we did earlier from 5 to 1 we did it. Identify the unknown displacements, there will be as many unknown displacements as the degree of indeterminacy. Find out the fixed end forces, that is you arrest the structure if any, meaning if you did not have any intermediate loads you do not have to go through this step. In trusses you do not need to go through this step of arresting because all your loads are always nodal, there is no intermediate loading there, it is only in beams and frames you have this. Then you express the element forces such as the beam end moments in terms of the displacements using a stiffness format. Remember we wrote that 4 EI by L into D1 and 2 EI by L into D1, so you have to go through this step. Then put it all together, identify the relevant equations of equilibrium of the structure as a whole, and so you have the F equal to KD equation, you have to bring it to this format. You know K, which is a property of the structure, F is given to you or you find it in equivalent terms, and then you invert that matrix and or solve it by some system and find the unknown displacements. You know the relationship between the unknown displacements and the end forces, so find the force response this way. There is a one-to-one correspondence between the path that the force method takes and the path that the displacement method takes, but they look completely different, but they lead to the same goal, and it's you should be comfortable doing both methods. Okay. Now alternatively, instead of solving simultaneously many equations, there are iterative methods which will give you directly the beam end moments. Okay. So the moment distribution method and Carney's method, unlike the slope deflection method, which we will study shortly, give you the moments directly. In fact, there is a question that is often asked, is moment distribution method a force method because you get the moments directly, you do not need to find any unknown rotations or displacements, and that is because you bypass the step of explicitly finding the rotations and calling this, invoking the stiffness relations, and just distribute the moment directly to the component beam elements. But the path is the same, the overall path is the same as this, it is just that in solving the equations you do not solve the unknown displacements explicitly and then substitute and get the moments, you bypass that and you solve it iteratively. So it is a displacement method because your governing equation is an equilibrium equation. So you need to know fixed end moments under various loading conditions. They are available in many handbooks. In the book that I referred to, it's all available in a table, so in practice you can look at these and pick them up, but you should know at the very least some standard load cases like these. The first load case is a concentrated load on a prismatic beam of span L, the load is W, so the fixed end moments will be hogging at both sides equal to WL by 8, it is symmetric. Second load case also you should know, if you have an eccentric load with those dimensions A and B, it will be WAB squared by L squared and WA squared B by L squared. These two formulas you should know. The third one is very easy, if your total load is Q, the intensity is Q and you have a uniformly distributed Q naught, then the fixed end moments are Q naught L squared by 12 or WL by 12 where W is the total load, which is Q naught, which is equal to Q naught into L. And the last case, if you wish, where do you get the triangular load? Yeah, for example in two-way slabs the short beams will get a triangular load component from the slab, so there the formula is 5WL by 48. Just remember these formulas, if you forget them, which is the fastest way of recovering those formulas? Conjugate beam method, which we have studied at length. Then there are some more load cases, you can skip all of them except the seventh one. Where do you encounter this triangular load distribution? Usually earth pressures on retaining walls or hydrostatic pressures. Okay. If the total load is W, remember it is WL by 15 and WL by 10. Obviously the higher value will be where the intensity is more. So remember those formulas, in case you forget them you can derive them, the others are not very important. Now you know the fixed end moments in beams which are fixed, but sometimes you can take advantage where the far end is a hinge, so it is a prismatic propped cantilever now, and you remember I used the notation earlier, I introduced this F naught AB to remind you that at the other end you do not have fixity, it is a release, right. Now how do you need a separate set of formulas for these, or you can pick them up from the fixed beam? You can pick them up from the fixed beam using a simple logic. Let us take the same beam and fix the end B. You are supposed to know the fixed end moments MFAB and MFBA. How is MF naught AB related to MFAB and MFBA? Well, all you need to do is to add to this another picture where you reverse MFBA, right? And when you do that, at the end A you will get a moment. What is the moment you get? MFBA by 2, we have studied that, right? And it will be anti-clockwise. So you get MFBA by 2. So when you do superposition, obviously this is equal to this minus that. If you say see it as clockwise positive, it will usually add up. And if it is a symmetric beam, or let us take a case like this, you can easily work it out. So it is easy to remember. If it is symmetric, it is even easier. What is it? It will be, yeah, the additional thing is a half, so the final thing is
3 by 4.
Come on, okay, this you can work out. It will be 1.5. You got 1 and you got half extra from the carryover. Is it clear? Easy to remember. So you must take advantage of this. Now let us quickly do the same problem we attempted earlier, but with not a concentrated moment at O, but with all kinds of loads all over the place, right? We will do it fast because you are not going to actually do problems of this kind, but I want to show you it is not difficult. You still have only one unknown rotation, theta naught. So here now, what is the first thing you have to do after identifying theta naught? You must arrest that rotation at O and you will get fixed end moments. You have to separate out those 4 beams. So let us take the first one. If you separate it out, now we are saying MFA naught will be having a negative value because we are taking a sign convention that clockwise moments are positive. So can you write down the value of MFA naught for this loading condition? It is equal to minus of 80 into 3 divided by 8, divided by 8, you are right. And what about the second case? Q naught L squared by 12, right. So you can write those equations. If you get one, you can get the other, it is symmetric. Remember, the left side will always be negative because it is actually anti-clockwise, and the right side will be clockwise. Do not mix up this sign convention with the sign convention of sagging positive and hogging negative, which we use when we draw bending moment diagrams. Is it clear? So do not get confused with that. Let me clarify. Our earlier sign convention was if you apply moments like this, it will bend like this. This is positive and this is negative. This is sagging, this is hogging, which we will still use when we draw bending moment diagram. So let this convention be there. Now for the sake of analysis, we are using a different convention. The convention we are using is clockwise, whether it is on the left or right, is positive and anti-clockwise is negative. Historically this has been the convention. So you will see this is positive as far as the beam end is concerned and this is negative. So using this convention, let us say you have a UDL Q naught L, you can write it, this is the correct answer, we all know that. But you will write MF, let us say this is A and this is B, you will write MFAB as minus Q naught L squared by 12 and MFBA as plus Q naught L squared by 12, and if by chance this n were to be a simply supported end, with the same loading A, B, Q naught, then the notation we will use clockwise positive is MF naught AB, and this will turn out to be minus 1.5 times this, which is Q naught L squared by 8. Is it clear? These are the sign conventions we will follow. After we draw the final end moments and free bodies, then when we draw the bending moment diagram, there we put plus and minus in the bending moment diagram. But for analysis by displacement method, we will follow this convention. Later we will reverse this convention for a very important reason, which has to do with vector algebra. Okay, but traditionally this is how it has been done. Is this clear? All of you are clear? Now the second case is interesting. We are trying to take advantage of that guided fixed support. So how will you solve that problem? So now we are saying, let us say you have a problem like this. Wonderful, you are right. Let us say this is Q naught, and say this is A, this is B, and this is L. I want to find out these values. What is MFAB and what is MFBA? Perfect, he is right. So remember, whenever you see a picture like this, it reminds you that there is a mirror image on the other side which will give us the same condition, because this deflected shape will be like this. And if we had a beam which was twice this length, 2L, with the same loading, Q naught, that would deflect in much the same way. And here right in the middle you have that condition of symmetry, which is usually shown like that. So you can work backwards. This we know, these answers do not change. This we know. Let us say this is B and this is C. So MFAB does not change. And if you remember, the bending moment diagram here will be, right, hogging, hogging, sagging. This moment is Q naught into not L, 2L the whole squared by 12. And what is going to be this moment in the middle? Well, remember, if it's simply supported, it's the same curve like that. What will be this value? Q naught into 2L the whole squared by 8. The whole curve gets lifted up by Q naught 2L by whole. So remember that. You might forget, but you remember. It's Q naught 2L the whole squared by 8 minus which turns out to be, that's right, by 12. If you remember the final answer, go ahead and do it straight away. 24. And it's important to note, when you break it up into two, this is going to be hogging, this is going to be sagging, remember. Does it make sense? And there is no shear here, but there is a shear force here, there is a shear force here, which will equilibrate with the UDL. Very interesting. Not very well known. Is it clear? So at the end of the day, what are the answers you will write? For this problem, MFAB will be minus or plus? Minus, it's hogging, right? Minus Q naught, not L squared. Again you are making the mistake. 2L squared by 12 and MFBA will be what? Well, you can write this equation if you wish. Is it plus or minus? Plus, it's sagging. It's plus Q naught by 24, which is just half that value. You got learned something here. Okay, so this is very interesting, and that's how we get those answers here. MFOC, you can see here, MFOC is minus Q naught L squared, 2L the whole square, right? L is 3, 2L is 6, and this is half that, and I think there is a mistake here. This should be, no, it's right, it's right, it's right. This is right, please note. This is sagging, which means it's this way, which means it is minus. It's right. Yeah, no, no, no. Look at this picture. This is sagging. So this is anti-clockwise, which in this sign convention should be minus. So this is a rare case where not only this is minus, but this is minus on the right side. Usually it's minus and plus. Left side is minus, right side is plus under gravity loading. This is one rare case where the right side is also of the same sign as the left side, which means both are minus. Is it clear? Have you understood? There is another rare exception, I might as well point it out. Let us say you have a concentrated load M naught right in the middle of a beam. The deflected shape will be right, deflected shape will look like that, and MFAB, what do you think the direction here will be? Clockwise or anti-clockwise?
Clockwise.
Well, this part looks like it's being lifted up, so it will be clockwise, and this will be also, no, it's being pushed down, no, pushed down, it will be clockwise. So this is another rare case where MFAB is equal to MFBA, and the answer is, it's worth remembering, is M naught by 4. Some standard cases worth knowing. Okay. In the table I have given you a generalized formula where that concentrated moment is located anywhere in the beam, but in the middle it will be M naught by 4. So far so good. Can we proceed? You take these two remaining cases, take this case. This case is this beam, this beam where you have a roller support on top. So this is easy to calculate. What's the answer? MF naught OB will be 1.5 times what? WL by 8. So 1.5 times WL by 8, and it's positive because you have to rotate it and then you'll realize why it's positive. Got it? Is it clear? Isn't it positive? Do you have a doubt on that? Not clear to you? No, okay. Is it crystal clear or not? Okay. So here you have a situation where that beam is vertical. You have a case like this, right? You have arrested this end, and this you propped, though it's shown like this. Where is your load acting? The load is acting here. What is the deflected shape? All this you should bear in mind. It's like this. So you can turn it over if you are more comfortable with this situation. Okay. Now you don't have any doubts. This is going to be always clockwise. Is it clear? Are you okay? So don't make mistakes with signs, it's very important. Got it? So MF naught, so all these are easy to calculate. Now if you add up all the moments that accumulate at joint O, you will get something. In this case you get minus 115 kilonewton meter. So this is the equivalent joint load which you can handle easily. Now let me take another case where, don't worry, don't take this down, just want to demonstrate, where you also have in addition a concentrated moment here and here of 45 kilonewton meter. Now this picture looks scary, is it not? But you are brave warriors who have learned displacement methods, and you will first recognize this is symmetric, and you will say if you cut one half, you will do what we did in the previous slide. The only change is you have an additional concentrated moment 45 which you have to add, and 45 and 115 when you add, because this you have to put negative sign, no, to add up, you get 160, and this we have done in an earlier class, and you can solve the problem. Is it clear? So you have to use your brain. You can't say I am sitting there, it is not coming naturally to me, until you have learned to master this subject. Clear? Okay, and you can just, so don't forget there is a fixed end force diagram which is here, which you are supposed to add to the diagram that you get from the nodal moment, then only you get the complete solution, because the actual problem is a distributed load problem, and don't forget to add that. One last point to note before we start the slope deflection method: what happens if you have, in addition to rotations, you have translations, right? In addition to rotations you have translations. So let us take the same beam element, and we have two types. Let us first say that one end is hinged and the other is fixed. So let us say you have a deflection at B relative to A of delta BA, which is the same as saying you have a clockwise rotation phi which is delta BA by L. So here the right support went down, here also the right support went down, but we flipped the two ends. Now this is fixed and this is hinged. Okay, so here the left end is fixed, here the right end is fixed. Can you draw the free body diagrams and the bending moment diagrams? What's the answer? Well, you can, we did it recently. What's the relationship? Okay, what are the values? What's the fixed end moment you get?
3 EI.
That's right. What's it?
3 EI.
Well, this is true. I mean, if you're going to have a downward reaction at B, this is true. What is P? How is it related to delta? Delta is PLQ by 3EI, you are right. So that is how you get this relationship, and if you substitute you get 3EI L square into phi, and this is your answer. Your fixed end moment is 3EI by L into phi, or 3EI by L square into delta. Is it clear? It is very interesting to note that you have a clockwise rotation here, but the moment you get is anti-clockwise, clockwise chord rotation. Now I want to ask you a question. This 3I by L is familiar to us. You get 3I by L in a propped cantilever when you apply a moment, unit rotation, the relationship between, is it not? There is a 3I. Is that 3I by L and this 3I by L related? Is it related? There you had a flexural rotation, here you have a chord rotation. Is there a relationship? Can you give a physical meaning to it? We will try. You try. So we will do it in a clever way. Let us say originally itself this was like this was straight, okay. Now what do you need to do to get the other picture? You have to rotate A in the anti-clockwise direction. That means you are now visualizing a rotational slip. You do that and you get the same shape we got earlier, and when you do this, what is the moment that you need to, what is the reaction moment that you get? 3A by L. So you know there is a one-to-one similarity, and this is very interesting, and you can use either interpretation and get the same answer. Similarly, if you have, we have done this recently, if you had both ends fixed, what is the fixed end moment that you get? Instead of 3ei by L into phi, you get, you do not get 4, you do not get 4, you do not get 3, you do not get ei by L, you do not get 2ei by L, you are trying all permutation and combination. Let us do it this other beautiful intuitive way, okay. We incline both the supports, we rotate one, when you rotate one, what is the moment you get there? 4ei by L, and what do you get on this side? 2ei by L. Then you rotate this also, what do you get here? You get 4ei by L and you get 2, what do you get totally? 6ei by L, right. So you forgot that number 6 and you can prove it. You can prove it, and it is very easy and very elegant. You can also do it from deflection, saying that the deflection in the middle is delta naught by 2, remember. So you can prove this easily. So in general, when you see pictures like this, you look for chord rotations. If the chord rotation is clockwise, you get an anti-clockwise fixed end moment. It is either 3ei by L if the far end is hinged, or it is 6ei by L at both ends if both ends are fixed, right, and vice versa. Okay. Now we start with the slope deflection method. Let me just introduce it to you. It was formulated by George Maney in 1915. It is the foundational method, it is where all the displacement methods started, and subsequently Hardy-Cross in 1930, he was a professor at Illinois, he suggested a simple method called the moment distribution method, and parallelly in East Germany Gaspar Kani proposed his method called Kani's method. Now throughout this we will assume a sign convention which I have already mentioned, that clockwise moments and clockwise rotations are positive. And you will recall this, that if you want to take advantage of reduced indeterminacy, then you can play with those stiffness values. It is 4ei by L, 2ei by L combination, or it is 3ei by L and 0, or it is ei by L and minus ei by L. Is it clear? So you remember this. Now this is how George Maney proposed this method. He derived some basic slope deflection equation for a prismatic beam. Now let us imagine you have a continuous beam or a beam which is part of a frame, it is the same thing, it does not matter. Let us take a continuous beam, and let us take some intermediate beam in that system called AB, right. You remember we wrote the 3 moment equation earlier, well it is similar to that. And let us imagine the worst kind of loadings possible, very messy intermediate loads. Let us also assume that this support deflected by delta A and delta B, and let us say the deflected shape is this funny shape like this for the beam element AB. We are trying to preserve in this shape some sign conventions. 3 sign conventions we have preserved for theta A, theta B and rotation, chord rotation phi AB, all are clockwise. The shape I have shown, theta A is clockwise, it is a flexural rotation, theta B is clockwise, it is a flexural rotation, and chord rotation for that entire strip phi AB is also clockwise. Can you see that? I have assumed delta B to be more than delta A. If delta B is equal to delta A, then that chord does not rotate at all, you do not have a problem, you do not have differential settlement. Is it clear? Now how do we, our interest is to write expressions for the n moments at A and B using, so this is what we want, this is the free body of AB. In the free body of AB you do not show displacement because you free the body from the external constraints. So can we write an expression for MAB and MBA from first principles? We can. How do we do it in displacement formulation? You have to first arrest your kinematically determinate structure is one in which theta A and theta B are both 0. So you do that, you catch hold of theta A, theta B, artificially pin them down, arrest them so that they do not rotate. Then due to the loads you get fixed end moments which you are supposed to know how to calculate, right. So no chord rotation, no flexural rotation, you know how to get MFAB and MFBA, clear. Next what do? Release theta A, see you are rediscovering, you are reinventing this beautiful method. So release theta A, let it rotate. When you do that, what is the moment that you get? Far end is fixed in this case, it will be 4 ei by L theta A and 2 ei by L theta A on the other side, agreed? So we have to superpose these, then we have to superpose 2 more pictures. What is the next thing we will do? Release theta B but arrest theta A, because we are going to do superposition. We will do that and you will get this, very straightforward. Finally you have to do one more picture. What is that? Take the primary structure and do not forget there is a chord rotation. Give that also, then that completes the picture. Fix them, allow that chord rotation, delta A comes down, delta B comes down, there is a rotation phi AB. And the moments are, if you have a clockwise chord rotation, you have anti-clockwise moment 6 ei by L into phi AB. Is it clear? Now can you write down equations for MAB and MBA? What will they look like from these 4 pictures? If you add up these 4 pictures, you get back the original picture both in terms of the force field and the displacement field. So won't they look like this? MAB is MFAB plus 4 ei by L theta A plus 2 ei by L theta B minus 6 ei by L phi AB, which can be written in this format. MBA is MFBA plus 2 ei by L theta A plus 4 ei by L theta B minus 6 ei by L phi AB. So we will stop here with this introduction. Thank you.